people in the country is known by the quality of the roads. So when we talk about the India, the road network, because there are many who are not highway engineers here, in India, we have nearly 62 lakh kilometers of the roads. Out of 62 lakh kilometers of roads in the country, national highways and expressways contribute to nearly 1,36,000 kilometers. State highways, 1,76,818 kilometers, and majority of the roads in the country are 59 lakh kilometers. Therefore, it is not the national highways alone that should be given attention. I will take you over what are the issues, problems, and challenges that are faced by the construction industry, especially by the civil engineers. Over 65% of the freight and over 80% of the passenger traffic is carried on roads. On average, the vehicles grow at around 10%, which means many of the single lane roads, single lane is 3.75 meter, multi-lane is each lane is 3.5 meters. So the single lane will become a 2-lane road, 2-lane will become 4-lane, 4-lane will become 6-lane, 6-lane become 8-lane and multi-lanes. So there is no dearth for a job for a civil engineer, especially in the highway engineering sector. These national highways, which are less than 2% of the country's road network, carry nearly 40% of the traffic. The issue is that we have identified the importance of improving the road network, increasing the road length, as well as improving the quality of the roads over a period of time. Today, we have nearly 68,895 kilometers taken up under the National Highway Development Project. So what is the issue here? How much is the investment? Around 55,000 kilometers, which are costing more than 6.26 lakh crores, is under progress today. So you can now imagine the quantum of funding that is being invested on the development of the roads. At the same time, we are investing more and more on national highways. At the same time, are we investing on the other quality of roads? We have excellent highways in the country today. Earlier, we used to say, go to other country of the world to see a good quality road. This Ahmedabad-Vadodara Expressway, which is comparable to any other road network in any other place of the world. We have beautiful highways. This is again from Chennai to Bangalore, constructed by L&T. The Yamuna Expressway, again a concrete pavement. So we do have beautiful highways in the country, which have been constructed in the last 20 years. We also consider the rural roads. Today, rural roads are also green, sustainable. So the issue at this point of time is that major problem that we face is non-availability of a good quality aggregates. That becomes the first challenge before all of you, all of us civil engineers. We want to construct huge infrastructure. Where are the materials? Do we have adequate quantity, good quality soil, aggregates, other materials? What is the cost of construction? So we find that if you want to construct either a 4-lane highway or for a 6-lane highway, a granular subbase requirement will be nearly around 8,395 metric tons. For a 6-lane, it is 14,373 metric tons. Granular wet mix macadam base around 10,000 for a 4-lane and 21,000 for the 6-lane. Then bituminous layers, bitumen, we require a huge quantity of materials, soil, and binders. It can be cement, it can be bitumen. How much is required overall? If you look at the overall requirement, we require around 170 million tons of aggregates every year. Considering a low growth scenario and a high growth scenario, we require nearly.
Okay, sir. We are able to see.
Good. Yeah. So we require nearly 450 million tons of aggregates every year. Do we have? If not, what? I think that becomes the first challenge before us. We can do all on paper on the blackboard that we can design, construct any structure, but we don't have materials. How are we going to construct this structure is going to be the biggest challenge. For the road development program, we require, as I was mentioning, 450 million tons of aggregates per annum, good quality aggregates, which are suitable for construction. Many of the states do not have these aggregates. Many of the states have banned quarrying. If so, how are you going to develop this infrastructure? And secondly, it's not only for the initial construction, during the design life, we may have to maintain the structure as well. So we require aggregates even for the maintenance as well. For many of the states in the north, you don't have good quality aggregates as we have in the south of India. For transport agri-construction in Bengal, aggregates are being transported from Bihar. You may be surprised to know that for construction of pavements, airports in Andaman Nicobar Island, aggregates are being transported by ship from the mainland. Northeast, not good quality aggregates. How are you going to construct? I think it's time that we look at artificial aggregates, new materials, or in a nutshell, how to reduce the virgin aggregate consumption. I was showing here for a 60-kilometer road section, which requires nearly about 20 lakh tons of material. For a lead of around 200 kilometers, I have to spend nearly 180 lakh liters for diesel alone. Now, think of the cost of construction, cost of material, cost of transportation. Then you have to add both the cost to work out the cost of the structure. There lies the major problem. What are sustainable payments here? Sustainable in the system in respect of payment refers to a system wherein you should be able to cater to the demands of the traffic above the desired serviceability level. What is the serviceability? What is that you want? If you ask me, you will say, I want a good riding surface. You should be comfortable. It should be safe. That's all you will tell. You will not tell whether I need a bituminous pavement, a concrete pavement, or composite pavement. What we need as a performance is that in quantified in terms of riding quality, in terms of safety, in terms of comfort. That's all finally we look at it. But this requirement is not only for the day you open the road to traffic, but our design life, which can be 15 years, 20 years, or 30 years. When I want this pavement to last for 15 to 20 to 30 years, will it last? And there's a difference in the pavement engineering, which you have to understand between any other structure. A structure may last for 100 years. A brick may last for 100 years. But will a pavement last for 100 years? Never. Why? Because of several complications involved in materials, design, construction, operation, maintenance, and management. I think the pavement is one which is abused by all road users. In spite of the fact that it's being used, overused by different vehicles, it has to give a smooth riding surface. How to do that? What are the different parameters that influence the performance? We'll talk about that. Secondly, the utilization of the materials, not only for the construction, the design life should be minimum as much as possible. In a nutshell, we should be able to conserve the natural resources, not only for the initial construction, but also during the design life. At the same time, we also want the life cycle cost to be lower. What is the life cycle? Life cycle means initial cost of construction, maintenance cost, road user cost, salvage value at the end of the life. All costs you put together, the life cycle cost should be the lowest. I'll tell you why it is important and what the role of a civil engineer. What are the strategies that are available? What we need is a given material when I want to use in a pavement structure, it should extend me a longer life. The time from the maintenance cycles should be minimum. Or in other words, if I want to construct a structure today, for next 30 years, next 50 years, you should not warrant major maintenance. Is it possible? What material should I use? That's again an area for research. It can be the binder, it can be the aggregate, it can be the mix. All selection plays an important role. But what I found is that what we do in the laboratory within the four walls doesn't work in the field. There is a wide range of variability when you translate the design to a reality. So quality of construction influences the performance of the pavement. Second, I have material, it can be bitumen, it can be cement, it can be aggregate. But when I want to construct it, how to ensure that the quantity of material that I'm using is minimum? Can I use the material again and again? Can I recycle the material? Maybe possible. If I want to recycle, how do I characterize a material? This is again another area for research, which I call with the term reclaimed asphalt pavement material called as a RAP. There are a lot of waste material available, like for example, tires, used car tires, truck tires. Can I powder them and use it in bitumen? Will it extend the life? What dosage? What should be the specification of the crumb rubber? How does it improve the performance? What will be the life of that pavement? So these are issues and challenges before us. Definitely, when you use different technologies, the performance will improve, likely to improve. But as a civil engineer, you should be able to tell what technology to adopt, what are the cost implications, how much will be the extended life, what is the maintenance requirement, and in a nutshell, what will be the life cycle cost. At the same time, when I want to use this material, what are the benefits to the environment in terms of reduced aggregate consumption? This again, a factor to be considered, but today we don't consider this factor. I think those of you who are attending the course with a specialization in environmental engineering should help the highway engineer to quantify the environmental benefits of using alternate technologies. I'll show some slides. So we should also be able to reduce transportation of large quantity material, which means I should use whatever material that is locally available. If the locally available material is not meeting the specification, how to improve the properties of the locally available material? That's going to be a challenge. Can a pavement be recycled? Yes. Can it be recycled again and again? Yes. How many times? Any number of times. What are the issues? That's again a challenge for research. There is a need for bringing in new machinery, new equipment. There are large quantity of waste materials available, alternate materials available, modular materials available. I think it's time that we look at all this material when we talk about the sustainability. And always make sure that the pavement performance is not compromised in any case. I can claim that I have used waste plastics in road construction. I can say that I have used fly ash. I can say I have used steel slag. I can say that I have used polymer. But will it guarantee you your satisfactory performance? That is the $1 million question that has to be answered. If you are a designer, will you stand a guarantee with the contractor saying that your design will work? We may or may not be. That's where we are at the crossroads today. So sustainable road infrastructure to consider stabilize upgrade. For example, this again, I feel that should be the order of the day. Any soil can be stabilized. Will improved soils upgrade improve the performance? Yes. Will it reduce the thickness? Yes. Will it reduce the maintenance cost? Yes. Then why are you not doing? It's not mandatory. But again, when you talk about sustainable infrastructure, it's time that we look at soil stabilization. It can be mechanical, it can be chemical, it can be used as any other stabilizer. Naturally, our carrying stabilizer is possible. Second, when you talk about bituminous pavement, the pavement is subjected to repeated application, subjected to a lot of fatigue. And a lot of fatigue effect, this pavement should not develop a crack. How to make it more elastic? If it's more elastic and a repeated load, there will be a rutting forming. At the same time, if you make it stiff, it will crack. So how to balance between rutting and cracking is another issue that has to be ensured. Thirdly, what we find is that most of the pavements that are constructed in the last 20 years, when they are exposed to atmosphere, the volatile matter in the bitumen will evaporate, the material will become hard, stiff, it will start developing cracks. Once you start developing cracks, water will enter. Water is enemy number 1, enemy number 2, enemy number 3. Once the water enters into the pavement, it will strip out the material, it will lower the strength of the bottom layers and will cause several deformation, deterioration, and rutting of the pavement. We can also use new materials like a foamed bitumen, emulsion, which are environmental friendly. We can use reclaimed asphalt pavement materials. Drainage becomes important. That's where I want the support of those from water resources engineering to help me to design a pavement structure which is drainable. Not only surface drainage, subsurface drainage as well. At the same time, when I want to maintain the road again and again and again, there are issues with respect to the issues of maintenance, what material, what thickness, The issue of what we are talking about is a perpetual payment. Perpetual in the sense it should last for long years, 50 years. Can a bituminous payment last for 50 years? Yes, possible. This is again a role of a civil engineer. How to design a perpetual payment which will last for 50 years. Bituminous payment. I'm not talking about a concrete payment. Concrete will last easily. But again, will the concrete last for 50 years without major maintenance? Advantages: less agreed consumption, improved performance, lower life cycle cost, lower vehicle operating cost. It's a win-win situation. So what is the optimal payment thickness? What is the optimal payment design? That is a challenge question before us. The first question I posed is the material. The second question which I'm posing is about the design. Huge quantity of materials are required. In the case of alternate design, it can be for a new pavement. For example, I want to construct a pavement, new highway, expressway between Chennai and Bangalore. Should it be bituminous pavement? Should it be concrete pavement? Can I use different materials within the given pavement layers? What will be the performance? What is the life cycle cost? So there are several options before you. I will show you what is the composition. What you see is something either black or white, but what is buried below, nobody knows. So there is a case of sustainability in new and existing pavement, wherein in the case of new pavement, I can talk about alternate designs with alternate materials. Remember, when you talk about alternate materials, I should be able to characterize that material. For example, we use a modulus value. When I use some different material, it can be a binder, it can be for a base course, it can be a soil. What is the modulus value of that material? Will this modulus value remain same for an entire life of 30 years? Will it vary? How will it vary? Will it affect the performance? How much will it affect the performance? These are issues and challenges. In the case of in-service payments, which are already constructed, they will warrant maintenance. Due to repeated applications of load, there will be wear and tear, there will be fatigue, there will be a failure. So when it fails, what material to be chosen for maintenance? Again, there are different options before us. What are those options? So the issue when I want to talk about new materials, new technology is number one, characterizing the material. It can be done in the laboratory, but when I translate this into the field, will I get the same modulus or strength? That is the first question. Second, how will it perform during the service life? In other words, we should be able to predict the performance of the system with the new material. When it will warrant a maintenance, what maintenance treatment? How many times it has to be maintained in the design life? What is the life cycle cost? This is something that needs to be thought about. As I was mentioning earlier, quality plays an important role. The design may be perfect, materials may be good, but when you miserably fail in characterizing a material and constructing it properly, the same material can behave properly, with the result that technology gets a bad name, but nobody says poor quality of construction. So finally, we have to manage this road infrastructure of nearly 62 lakh kilometers. How do we do it? That's the question. To start with the new material, the pavement that we are constructing can either be a bituminous pavement, or it can be composite pavement, or it can be concrete pavement. I posed a question. When I want to construct an expressway between Chennai and Bangalore, should it be a bituminous pavement? Should it be a composite pavement or an inverted pavement? I will show what it is. Or should it be a concrete pavement? So never today, in the present scenario, what we do is that any agency for that matter, either Karnataka Road Development Corporation or PWD or National Highways or State Highways, they will tender it. I want to construct a road. There are contractors who bid for the work. Whoever quotes the lowest L1 will be awarded the work. The question which I'm posing at this point of time is that one sustainable? How many years will it last? If I want to have a design life of 30 years, how many times the payment has to be maintained? What is the maintenance cost? Do we have a material for the maintenance? These are other questions that are to be answered. There are several factors that are to be considered, like engineering factors, material availability, equipment availability. You have to work out the life cycle cost of alternate designs and sustainability into consideration. But unfortunately, in the present system of awarding tenders, we don't consider the issue of sustainability. I think it's time. That's why This training program will enable you to think differently as how to characterize a material, use that property in the design, how to predict the performance, how to estimate the maintenance requirement, and decide the choice of maintenance treatment, and in a nutshell, work out the life cycle cost. Today, the contract system has changed. All this time, it used to be the BOQ, bill of quantities. You decide this road, this should be a thickness, you call a contractor, contractor constructs. 1 year is a defect liability period. After 1 year, 2022, this year if he constructs, he vanishes. By 2025, the payment fails. Then we thought that will not work. This BOQ will not work. Then we brought in an engineering procurement construction contract, EPC contract, wherein the contractor has got an alternate design possible. Today, many of the NHDP projects, National Highway Development projects, are under the category of design, build, operate, and transfer, which means I'm only saying that Chennai-Bangalore highway has the expressway has to be constructed. I only give you the land free of cost. You have to choose, it can be bituminous, composite, or concrete. But in the road, I will define the performance requirement. Performance, rutting should not exceed 10 millimeter. Cracking should not exceed 10% of the paved area. Riding quality should not exceed 2000 millimeters per kilometer. That's all I will tell. I will come and measure any time of the year. You bury whatever you want. Now, the contractor who is bidding for the work now will think double or thrice, will my design work? Should I use a new material? If I use a new material, what is the life of the payment? What is the maintenance requirement? What will be the riding quality that it can offer? So we brought in innovations in the use of new materials, technology, construction practices. And today, many of the contractors are adopting new materials and technologies. There are other projects which are under the toll, operate, and transfer. Now road is available for sale. If you want to buy a road, if you have money, some 500, 600 crores, if you have money in your pocket, you can come to me. I can tell number of projects that are available for sale. The issue is not that buying the project. The question is that you have a road. It has developed some cracks, some rutting. Today it is a road in operation, 5 years old road, 10 years old road. I want to maintain the road for next 30 years. Now you should evaluate the existing pavement, work out that is structural condition, functional performance, and again think in terms of new techniques, new materials, technologies for the rehabilitation of the pavement. So the challenges are interesting and many times more. A bituminous pavement may consist of different layers. What we see is a black top here. Below that you have a base, a sub-base, a subgrade, and a fill can be in cutting as well. So if you want to upper the performance of the pavement, it's not this layer alone that matters. Bituminous bed layer again there are sub layers here, a wearing coats, upper binder coats, lower binder coats. Base coats can be granular. It can be cement treated. It can be bitumen treated. Again, there are choices. Sub-base is essentially a drainage layer. It should also distribute the load over a wider area. Subgrade can be conventional subgrade, or it can be a modified subgrade, or I can call in a nutshell as an engineered soil. That's what I think we should never talk about stabilized soil. We should call with the term engineered soil. Earlier, what you used to say is design a pavement for 5% CBR. Design a pavement for 10% CBR. Now, what CBR do you need? 30, 50, 20? What is that you want? I can give you the strength. Will the improved strength of subgrade result in reduced thickness? Yes. Will it result in reduced maintenance cost? Yes. Performance in better? Yes. But the thing is that finally, when you talk about sustainability, when you want to reduce subgrade consumption, improving subgrade is a simplest solution. The cost of soil may be 200 rupees per cubic meter, 300 rupees per cubic meter. This bituminous layer, which is the top, costs nearly 40% of the total pavement system cost. So if you want to reduce the cost of construction, then simplest is improve the subgrade, engineered subgrade soil, reduce the thickness. Again, this base cost is 250. Can I reduce? Yes, you can do it. Sub-base 200. Can you reduce? Yes, I can do it. That is where the sustainability comes into picture. That's where your challenge starts. What should be the design? The basic principle of pavement design is that we talk about the vertical compressive strain on top of the subgrade. and the radial tensile strain at the bottom of the bituminous layer. This causes a bottom-up cracking of the fatigue crack, and this results in the rutting of the pavement when it is become excessive. In a nutshell, your design should be such that this strain value should be within the allowable limit during the entire design life so that crack does not form. And this vertical composite strain should be within the allowable limit so that no rutting will form. How to do that? What are the alternate designs? Normally, we require about 200 millimeter of granulus of base, 250 millimeter of a base course, and 145 millimeter of a bituminous layer. When you have these layers in a pavement system, instead of reduce the thickness, I can have a cement treated base. In the earlier case, I talked about a granular base. Now I have a cement treated base. You can find the thickness of bituminous layer from 200 millimeter has come down to 50 to 75. We express the traffic in terms of million standard axles in the pavement design. A highly traveled highway can carry up to 150, 200, 300 million standard axles during the design life of 15 years. But majority of the roads in the country do not carry 150 million standard axles. But when I want to construct a pavement, I want to ensure that the maintenance requirements are minimum. Performance is good. That is possible by adopting this inverted pavement or a composite pavement. So what we thought is in the IICTE 37, we introduced new choice designs with a new design where I introduce a cement treated sub base and a cement treated base. At the same time, as a civil engineer, you should know the problem. You should also know the solution. What is the problem? The problem is that any cementitious layer, I don't call it cement treated layer, I'm calling cementitious layer, is likely to crack. When this layer crack, the crack will propagate to the upper layers. So due to repeated application loads, one truck may be 8 tons, next may be 10 tons, third truck may be 20 tons, fourth truck may be 30 tons, which cannot be predicted. When a heavy load, but we remember the design is for considering 8.2 tons, is the design axle load. But trucks carry 10, 20, 30, 40 tons as well in axles. When there's a repeated application of axle loads take place, the pavement will crack. Initially, it starts with a single crack. It's a bottom of fatigue cracking. Again, the crack will become more crack propagation phase or effective fatigue phase, and again, it'll become an equivalent granular phase. Now, why I'm bringing this is that initially, when it was uncracked, it had some modulus value. With a repeated application, it started developing cracking. And today, as maybe at the end of 5 years, 8 years, 10 years, it will reach a stage of granular state. The modulus of the cementitious layer, which was 5,000 initially, will become 1,000 later. How do you consider that in the design? That is what the challenge before you. How many years will it reach for a pavement to reach a granular state in terms of modulus? What is to be done? I can prevent these cracks will reflect on the top. I can have a crushed stone base as a cushioning layer above, which will prevent the crack from propagating to the bituminous layer. That is called as a crack prevention course. So as a civil engineer, you may do a PhD on a cement treated base, but you should know how to use it in a pavement system. What are the implications? What are the causes, pros and cons? Definitely it will crack. You should take precautions when you do this. We brought in another catalog wherein cement treated sub-base, cement treated base is having a granular layer, which I showed in the earlier case. We can have bitumen impregnated geosynthetic called as a SAMI layer, stress absorbing membrane interlayer, which will again retard the crack from propagating to the top. I can have reclaimed asphalt pavement materials. Again, I'll take you up what is the wrap material. You can have another catalog for a granular sub-base, cemented treated base, and aggregate layer. And I can also have cemented bases with mixed macadam. So what I want to bring in at this point, showing all the 6 catalogs, is that pavement design is not one design. You have different options for the design. But the challenge before you is to tell how to characterize the material which are used in different layers, use that material property in the design, predict the performance, identify in which year it will warrant a maintenance, and in a nutshell, what will be the life cycle cost. That is the first challenge before you. I can go in for a concrete pavement. Again, it will have a base course and a sub-base. Why are you not going for a concrete pavement? Don't go for concrete pavement because cost is high. How much high? Is the life cycle cost lower? Yes, the cost is lower. But I don't prefer a concrete pavement because of the fact the initial cost is more. How much more? Today, I can give you a design wherein the initial cost difference between a bituminous pavement and a concrete pavement can only be 20% more. It doesn't warrant a maintenance for 30 years. But there are issues and concerns here. There are different types of concrete pavement as well. It's not one design I was talking. It can be jointed plain cement concrete pavement. It can be continuously reinforced concrete pavement. It can be fiber reinforced concrete pavement. It can be precast concrete pavement. There are a number of types again as well. It can be even jointed as well. But the load transfer mechanism is different. It requires lesser thickness. It takes the load by the slab action. With the result, even the soil is poor, we can go in for a concrete pavement, which will last longer. But at the same time, we need sustainable materials. Sustainable material in the sense which will have a higher modulus. Conventional aggregate we have. I said the thickness requirement is 250 millimeter of a subbase, 300 millimeter of a base course. Can I reduce thickness? Yes, possible with that materials. I need a high modulus base. What is that high modulus base? Again, an area for research. Now, as mentioned by the Vice Chancellor, the polymers are available. Using a polymer, we can develop a high modulus base. If I use a high modulus base, thickness can be reduced. Performance can be improved. Again, another area for research. It will withstand repeated applications of strains and not crack. How much more repetition it can take? Again, an area for research. How much will be the thickness reduction? Again, another area for research. So these are the new areas of research which you should learn by attending such training program. Because I'm reducing the maintenance requirement, the pollution levels are decreasing. Can I count this in the project evaluation alternate design? Yes, that is what is required. Will there be saving in cost? Yes, there is saving in cost. How much? That has to be quantified. We can use the milled material again and again. And what is the percentage of milled material that I can mix with the virgin material before I use in reconstruction? So simple technique is reduce, reuse, and recycle. That is what we are now moving around. But again, civil engineer has got a different role on characterizing the material. Even simple example, if I have a pavement which requires nearly 595 millimeter thickness for a substitute of 10% with 50 million standard axles, it will require 15,000 metric ton per kilometer for a 2-lane highway with a paved shoulder, 15,000 metric tons. Other hand, if I have a rigid pavement, I require only 12,935 millimeter. I can reduce the aggregate consumption. If I can, simple, I don't do anything more. I don't bring in a new material in the upper layers. I am only stabilizing subgrade. Is it beneficial? Yes. What's the benefit? Instead of providing a 140 millimeter binder course, I can reduce thickness to 105. Thickness reduction can be of the order of nearly 30 plus 39 lakhs per kilometer. So it is possible, just soil costs nothing, but improved performance is possible by stabilizing subgrade. Even in the case of lower volume roads, if having waterborne macadam with a granular base, I can mill the material, stabilize it with a stabilizer. You'll find that from 2,365 cubic meter of aggregates, I can bring down to 252 cubic meter. There's a significant reduction in the cost possible. Therefore, if you talk about sustainable practices in civil engineering, in road construction, simple solution is adopt stabilized subgrade, stabilized subbase, stabilized base courses. A road which was like this can be made good like this by introducing stabilized pavement layers. Look at the composite pavement or inverted pavement, you will find that I can reduce thickness of bituminous layers to 50 to 75. When you talk about the different designs possible, you'll find that instead of having a granular subbase, I can have a cement-treated subbase. I can have a cement-treated base. I can have a granular subbase and cement-treated base. Now, as a civil engineer, you have to quantify what is the aggregate consumption or virgin aggregate that is required for all these 4 different types. You should be able to predict how they will perform. You should be able to predict what is the maintenance requirement in terms of aggregate consumption, in terms of road user cost because of bad roads, in terms of life cycle cost. And there lies the challenge in terms of sustainability. We can look in terms of most common is cement treated subbase. Instead of granular subbase, go for cement treated subbase. For a design life of 70 to 150 MSA, the wet mix macadam, which I'm providing here, acts as a crack relieving layer. This crack will propagate to the top. So you should know the problem, you should know the solution. But you can find the thickness reduction is significant. It's possible here. I can quantify and show here. So what I do here is the cement is well-known product. You spread, I don't require a huge quantity of cement as well. 2%, 3%, 4% may be adequate. You spread the cement, pulverize the material, compact it in layers, grade it and cure it over. You can reduce the thickness from 250 millimeter to 150 millimeter. You can now work out the savings in aggregate. It will definitely result in improved performance as well. This is for a project in NH 344A for a 10% CBR and 90 million standard axles. They worked out what the cost, the pavement layers. They found that so having a dense bituminous macadam of 5 lakh tons, we can bring down, and a wet mix macadam of 720 lakh tons. We can bring it down significantly by adopting a cement treated base. You find that the benefits in the case of adopting the new material is in terms of reduced thickness. You can find the thickness drastically reduces. Strain values have to be checked. If you want to check the strain values, you need the material property. What the modulus? What is the change in modulus during the design life? So this will enable you to work out alternate designs. This method of design is called as a mechanistic empirical design, wherein I compute the stresses and strains of the pavement layers. I relate these strains to the performance in terms of rutting and cracking. There are allowable strain values. This is again has to be cross-checked. Certainly, 22% reduction in the thickness possible. You can find that savings in the quantity of aggregates is of the order of nearly 60 lakh rupees. In the case of cement treated subbase, nearly 27 lakh rupees. Nearly 6 million rupees savings per kilometer is possible by adopting alternate design. Now you have no choice. For sustainable practice, you don't have the luxury of having the thicknesses which I showed earlier. We have to cut the leg to the shoe size. With the available material, how do I design the pavement? So now civil engineers are in great demand to come out with alternate designs. You can find that nearly savings in cost is nearly 65 lakh or 6 million rupees per kilometer. You can work out and check what are the benefits. So if you want to use the material again and again, recycling is one of the several alternatives that is available today. So when I have a pavement condition which is start deteriorating from the day it is open to traffic, it becomes very good, it becomes good, it becomes fair, it becomes poor, it becomes very poor. When the pavement reaches sometime during good and fair, I can mill the material, recycle it, and rejuvenate the pavement so that the performance pavement is really much, much better. So this question of recycling, it can be done by different approaches. Whenever you find the riding comfort is not good, there's an excessive distress in the pavement, reduced friction, large maintenance cost, road user cost is higher because of the bad roads, structural capacity of the pavement is inadequate, you can go in for recycling. You have to select the recycling method. What I'm trying to do is that I'm trying to mill the material which has already been buried. Conventionally, what you do is you provide an overlay at the top. I don't want to do that. I want to mill the material and reuse it again. So when I want to mill and reuse the material, this milled material will have aged bitumen, aggregates. We can rejuvenate the material and use it again. Again, there are 4 different types. 2 broad types, hot recycling and cold recycling. Again, it can be in place recycling or central plant recycling. Again, there can be full depth reclamation. The civil engineer has to decide which is the most appropriate method, which is sustainable. That's where the challenge is. Not just design, but you should be able to predict the performance, quantify the benefit of the new design, new materials. Hot mix asphalt can be used when there are surface defects, as I was mentioning, the top-down cracking, deformation, cracks. So, but how much milled material, which I showed in a video, can be used? That again depends upon limitations of the plant. In the case of a hot mix drum mix plant, we inject the virgin aggregate to a drum mix and use the reclaimed asphalt pavement material here. This already aged. I don't want to heat it again. So this aggregate will in turn be first heated. This hot aggregate will in turn heat the wrap. So unless this is 70%, it will not be able to heat this 30% material. Therefore, considering the plant limitation, we do not permit more than 30% of the wrap. But I have 100% wrap. How do I use it? That is the question. That's again a research need. How do I characterize the reclaimed asphalt pavement material such that it can be used, 100% can be used in a recycled mix? That's a challenge, again, area for research. What rejuvenator? How do you rejuvenate the material? Will the aged binder be made good like a virgin binder? This again another area for research. Now double barrel drums are available. When I don't heat the wrap material, I inject the material into the drum. There's an inner drum and there's an outer shell, another drum, outer drum. So this material gets heated. They go to the outer drum after adding the bitumen. In the outer shell, you add the wrap. With the result, I can increase the percentage of wrap, which was 30% in the earlier case. I can increase to a higher percentage. But how many plants are available in the country? What are the cost implications? Is again, you have to study. I can use 100% material as an in-place recycle. When there are corrugations, surface retting, longitudinal slippage crack, I can mill the entire material, add virgin material to a less quantity, recycle, and relay it back. So what I try to do here is that it is like an equipment frame. I heat the material, then I mill the material, I mix with the virgin aggregate and pave it back. So all in one operation. Case of a heating, scarifier, and a pug mill, and that material is laid. So when the equipment train moves by 1 kilometer, you have a newly laid pavement. So again, characterizing the material used in the wrap, design of the mix, thirdly, design of the pavement with this reclaimed asphalt material, predict the performance going to be a challenge. It was done in NH45 in Tamil Nadu by Hitachi. Again, the company is in Bangalore. This for heating, it will heat the material, surface layers, but what thickness? It can mill 50 millimeter, 70 millimeter, maximum 100 millimeter, but not more than, generally not more than 50 millimeter. So if your distresses are confined only to the top 50 millimeter, you can mill, heat it first. After heating, you mill the material. The milled material will have lumps, fines will be missing, so to bring in, add the fines, and then lay it back. So hot in-place recycling also becomes an alternative before you to rejuvenate and recycle the material. It's possible you can go in for environmental friendly cold mix. Again, it can be done as central mix. Wherever the lower layers are deteriorated, I can mill the entire material. I can add a virgin mix. I can add an emulsion or a foam bitumen and then use it again. I can also do cold in-place recycling. In a central plant, I mill the material, add virgin binder, recycle, lay it back. I'll show you in a video clipping. This is what is called as the foamed bitumen. To the hot bitumen, I inject water, I inject air. The bitumen foams. When the bitumen foams, to the milled material, when we add this foam bitumen, it will try to mix the material which is being milled. So, and it's being laid. And so now you get an excellent base coats, which is much, much better than conventional granular base. So I have rejuvenated the material. I have reused the material. I have reduced the virgin aggregate consumption. I have given a new life to the aged asphalt. With the result, we found that the pavement can last longer. I did this for the first time in Chennai Tada Highway, NH5, near IIT Madras. I did this in the year 2011. 10 years are old, NH5, no maintenance, no rehabilitation. Today, even today, it's working fine. Based on the experience which I gained, we developed a code, IRC 120, is a new code based on the experience that we gained by adopting the cold mix technology. So we can mill the material, patch it, or I can provide an overlay. Normally, we provide an overlay like this. That's what you do across the country. But what will happen is that this will develop a crack at the top. So what they do is they provide a ultra thin friction course for 30 million standard axles. Constraint cost may be $30. I can mill the material, which is cracked. For the same traffic, I find this will cost nearly $45. I can do a stabilization, cement treated base of the whole pavement layers, provide a granular layer, and provide a hot mix asphalt. This will cost $42. So now there is again, I was talking about different alternate methods of design. Now I'm showing before you different alternate methods of rehabilitation of a pavement. All will have different cost. All will have a different performance. So I can also provide a thin layer of 35 millimeters. You will find the cost of this will be $24. Now, civil engineers have to tell which technology to be adopted for a bad road. Stabilize, recycle, rejuvenate, hot mix, cold mix, in-plant, central plant, what I should do now. You have to now tell to the agency for a sustainable infrastructure. Looking at that material construction cost wise, the bitumen stabilized material coal recycling is the lowest. I can find that when I look at the cost, alternate rehabilitation cost, we find that recycling is the cheapest. When a pavement is like this, fully cracked, heavily loaded trucks, what should I do now? You can mill the material. There will be lumps. These mixes which are having lumps will not have fines. We need fines to ensure a good stability and compaction. But without damaging the lower layers, I have to mill. So the lumps are generally thrown away. These are black gold. Why to throw it out? So you can mill the material. Now milling machines are available in India. You can mill any thickness that you need. 5 millimeter, 10 millimeter, 30 millimeter, 50 millimeter, 100 millimeter, it can be milled. So this milled material is taken to a central plant. You can reuse them either 100% in a cold in place recycling or a higher percentage or lower percentage in the case of hot in place recycling. So if they say depth, this is how your surface will look like. You'll have a better bonding and then no crack from the bottom layer will propagate to the top. So in the case of rehabilitation, either I can mill the top layer alone or I can mill the top layer and the base course as well. This is called a full depth reclamation. For sustainable pavement, I am rejuvenating the old pavement, which is deteriorated. I am adding only maybe 10% virgin material. I can use the whole bitumen layer, which may be 3% binder, 3.5% binder. I had to add only 1 to 1.5% binder. So I am reducing the cost. I am rejuvenating the pavement layers. I am improving the performance. So for sustainable infrastructure, the order of the day is to reduce, reuse, and recycle. We find that we can save a huge quantity of material. 100% recycling should be the order. Again, this depends upon the research that you carry out as how the material can be characterized, designed, and constructed. So the rehabilitation options, there are different options before you. When you find a thin layer, the crack will propagate refraction crack. Up to 30% wrap is possible in this case, but in a hot recycling. But when you want to have a cold recycling, 100% of material can be recycled. So there are different options before you, even for recycling. So in the case of a number of projects have been taken up in the country, I think several hundred kilometers are being recycled, reconstructed here. This again a highway. It's a shame to say that highway failed, but this highway failed in 3 months. Whatever distance you're saying is in 3 months. Out of spending 2,400 crores, not 1 crore to 2,400 crores. It failed, it cracked. There are several reasons for that. I also investigated the failure. I gave a solution. My solution costed 130 crores. Agency did not want to do that because they say my cost is higher. They delayed and delayed and delayed. Today, the cost of rehabilitation is 450 crores just for repair and rehabilitation again. Will it last? How long will it last? This is the challenge before you. So instead of having the conventional design which failed, now they are bringing in a bitumen stabilized material with a thinner layer, but you have to wait and watch. Will it perform? So again, you have to give alternate design for rehabilitation. So you find that overall cost savings by adopting this recycling technique is nearly about 110 crores, which the agency gains by adopting the recycling technology. We find that Total overall cost is nearly 900 million rupees, 90 crore rupees, by adopting coal recycling with a bituminous concrete layer of 50 BC. So we never teach all these to students. I think it's time that we teach all these to students so that they will think differently. They can be entrepreneurs in adopting, bringing in this new technology in road construction. We find that overall, for a 50 kilometer of 4-lane highway, the savings is of the order of around 200 million rupees, nearly 18% saving is possible. But we am talking only savings in construction material cost, but I am not talking about the environmental benefits that I bring in. That's again an issue that has to be addressed. Coal recycling can be used, 100% recycling is possible. We don't require solid waste disposal. It's a major problem in the country. 90% reduction in transport volume, nearly 90% reduction in the resource consumption, 50% reduction in the binder usage, 50% shorter construction period, and 50% reduction in the overall cost. So that is a sustainable technology that has to be adopted. I think it's time that we also look at outdated materials. I think it's time that we look at geosynthetics. I'm a fan of geosynthetic materials. These geocells can be effectively used. I have demonstrated that they can be effectively used. They are UV stabilized with carbon black. What are the benefits? I did a project for a typical project in Maharashtra. Geocell can be stretched, laid, filled with aggregates. What are the benefits? By adopting this geocell in the granular layer, if I have got a thickness of 975 millimeter, if I use a geocell as a subgrade, I can bring down thickness from 975 to 735. If I use it in the base and subgrade, I can bring down thickness to 520. If I use in the base course, I can bring down to 865. This lasts only 100 million standard axles. This can last for 150. If this costs 2,635 rupees per square meter, this costs only 2,450. Not only for a low CBR, even for a high CBR. Instead of having 650 millimeter, I can bring down thickness to 340 using geocells. They provide the confinement. You see here, they provide the confinement that you need. There are perforations. This enables drainage. As I was mentioning, subsurface drainage is possible. Instead of having 250 millimeter for granular subbase, you can bring down thickness to 100 millimeter, maximum 150 millimeter. It enables the water to get out. Confinement is there. Significant reduction in the thickness, improved performance, and lower life cycle cost. It's time that we look at the new materials. This is again a case of a project road in Bhavnagar. So the soil here is a high water table, high flood level. Soil had a CBR less than 2%. Traffic was 65 million standard axles, 15 years recent life. That was the soil. Now you have to construct a sustainable pavement here. These are the initial construction. So what is to be done here? Sustained solution is to take care of the confinement, take care of the reinforcement, take care of drainage. All this possible by having an extruded geogrid here, a drainage composite here, a road mesh here. So by using non-woven geotextiles, extruded geogrid, drainage composite, and road mesh, I can bring down the cost, improve the performance, and reduce the life cycle cost. Therefore, sustainable road infrastructure means adopting new materials and new technologies. Even in the case of low volume roads, we have started adopting fire and jute. It has got different functions of separation, filtration, drainage, and reinforcement. One of my students just she will submit her report today or tomorrow. We find that the thickness of the layers can be reduced significantly by using fire. From if I use 700 GSM, I can bring down a savings in quantity of 200 cubic meter per kilometer. If I use 400 GSM, I can bring in a savings of 100 cubic meter per kilometer. The thickness can be brought down. Instead of having 175, I can bring that to 135. Instead of having 775, I can bring that to 150. So significant reduction in aggregate is possible, improved performance, lower life cycle cost. It can also be used for erosion control. Concrete pavement again can be used, definitely lower rate of deterioration, longer life, lower life cycle cost, lower thickness, good night visibility. But under overload condition, again an issue, again you have to play a role as how to design a concrete pavement to withstand the repeated application of traffic loads. Stage construction is not possible, or it may get polished, it may warrant diamond grinding. Utility cuts, they say not possible, but now it is possible here. I think sustainability, if you talk about concrete pavement, is sustainable when compared to any other bituminous pavement. Low deflection, less fuel, 100% recyclable, low energy footprint with respect to production, delivery, and maintenance, optimal texture depth, lower life cycle cost. Therefore, sustainable civil road infrastructure is a concrete pavement. It can be adopted or for all categories of roads, from rural roads to highways. Right, the technology that we have to move in should be a precast concrete pavement. I think this is something you should teach and you should practice this. We are trying to bring this technology to Bangalore. Maybe sooner or later we will be able to come out. We have started developing this technology. According to me, today the road should not be there. Tomorrow morning when you come, there should be a concrete pavement. Is it possible? It's quite possible. So this pavement, concrete pavement, can be cast elsewhere in a yard, cured perfectly, brought to the site, and then assemble them back. It can be post-tension on the site. The road is being constructed in Nagpur today. So but there are issues and concerns with respect to the joints, ensuring a perfect level surface, connections. There are other issues that are to be sorted out. We are over a period of 2 to 3 years, we have been trying to sort out this problem. I think we will be successful in the years to come. White topping, we have brought in the importance of white topping in the urban roads. When the road is bad or bituminous pavement, I can construct a white top pavement. Thicknesses can vary. It can be conventional white topping, thin white topping, or ultra thin white topping. So definitely for sustainable road infrastructure, white topping is going to be the order. Mechanical empirical analysis suggests the low stresses depend upon joint spacing. So the rule of thumb is that thicker pavement, larger panel size. Thinner pavement, smaller panel size. So stresses are being transmitted directly. So the design approach is different. There is no slab action, with the slab size become lesser. You'll find that there is an optimal thickness based on life cycle cost. The lower thickness is not the one that will have a lower life cycle cost. Initial cost may be lower, but maintenance cost can be higher. But the other one, which has got an optimal thickness, will have a lower maintenance cost. Again, a role of you to come out with an optimal thickness. Optimal joint spacing has to be worked out. Again, we should look at green highways. Use of warm mix asphalt, reducing the production of the mix. Environmental management, use of locally available material, natural cut slopes, recycled material. Again, I think we should look in terms of storing the water, saving the water from the pavement into the rainwater harvesting approach should be adopted. I think again, environmental and water resource engineers should help us. Long-lasting pavement, lower life cycle cost is going to be the future. So to conclude, what we need is lab and field studies on new materials, alternate materials, and translate theory to practice. You should consider the constructability issue. In a lab, you may take 1 kg of soil, 5 kg of soil, exactly pour 65 grams. You can pour 65 ml of water, mix it in hand. But when you do your site, go to your site, I may construct 1 lakh cubic meter of soil to be compacted. Where is the OMC? How the density will vary? How does it influence the performance? So you have to translate theory to practice. We need to construct test tracks using alternate materials. I think you should be able to, what I call by the term, instrument these pavement sections. That's where interdisciplinary research plays an important role. Predict the performance. Consider the constructability issues. Bid documents should consider the environmental benefits. We have to improve the capacity of the agencies to evaluate alternate bids. We need a feedback mechanism whether alternate technologies are working or not. So finally, to summarize, the future for sustainable road infrastructure is use of new materials, alternate materials, because we don't have the luxury of adopting the conventional approach. I think it's time that we teach these technologies, materials, characterization to our students. When you have new materials and new technologies, the design approach has to change. The material performance will change. So your design approach will be different. So alternate design of the new material is going to be a challenge, again, an area for research. We need an accelerated construction. We want to construct nearly 40 to 50 lane kilometers in a day. We want to go faster. How do you do that? Therein, the pre-cost construction definitely will play a role. There are technologies for preventive maintenance which can extend the life of the pavement. What technology, what material, How much is extended life? What are the cost implications? Again, an area for research. Whatever we do, we have to evaluate the performance in the field. Which technology to be adopted to evaluate? There are a number of equipment available to evaluate the performance, structural condition and the functional condition. When you use different equipment, there's a need for harmonization of different equipment. So there is again another area for research for sustainability, looking at which equipment to use, how many times you to measure the performance, how do you predict the performance and relate your predicted performance with the observed performance. Only then theory is translated to performance. You should be able to work out the life cycle cost and also work out the environmental benefits because of this sustainable technology. I think it's time that you should make the world more beautiful. You should leave the world more beautiful than what you found when you were born. Then you have done some service to existence. I feel all of us should work together to bring sustainability in construction, but the issue is that it's impossible to make sustainable environmental changes unless there's a change in the people's behavior, values, and philosophy of life. So first, you should change yourself. You should accept the new materials. You should accept the new technologies. You have to prove that they work. They are sustainable, long-lasting. If we can successfully accept the changes, definitely we can bring in sustainable infrastructure. I'd like to thank the IRC for enabling me to grow, learn in the process, and bring in and share my thoughts. Sustainable strategies for flexible payment from the presentation from Illinois. Professor Rajiv Malik, my colleague, who shared some of his thoughts, experiences. Federal Highway Administration, and also FIBNENS for his presentation slides, which I used liberally in my presentation. So thank you very much. I look forward to interact with you. If you have any questions, you can feel free to ask. Thank you.